Hi, I'm Malone and I'm going to be presenting to you today our work on boosting the performance of a baseline visual place recognition technique by predicting the maximally complementary technique. Visual place recognition is the task of matching a query image to a reference image from the same location in a previously captured database of images. Current literature shows that the best technique can vary significantly between different datasets depending on the conditions. Recent works have shown that fusing multiple techniques in visual place recognition, or VPR, can significantly improve performance over a single technique. These are methods such as hierarchical multiprocess fusion or shared representative learning. Furthermore, some techniques have been shown to be much more complementary for performance than others. Whilst effective, these approaches share some limitations, such as the best technique combinations must be calibrated for individual datasets, and they do not account for changes in the optimal combination within datasets. However, it is by nature a very difficult problem to find a combination of techniques which is performant across all datasets and to choose the optimal combination frame by frame to account for changes both between and within datasets. Our solution is to reduce the problem to choosing one technique to fuse with a given base technique. We train a multi-label classification network to predict the most complementary additional technique, and then use multi-process fusion to fuse the base and additional technique for visual place recognition. This gives us a method which allows us to change technique pairs on a frame-by-frame basis, is not dataset specific, and can be used on completely unseen datasets. In our approach, during training, we take a base technique and we retrieve the descriptors for the query and ground truth reference image. In our experiments, this is NetVLAD. We then take the difference vector between the descriptors as the network's input. Using binary cross-entropy loss, we then train the network using multi-hot target labels, where the multi-hot target labels indicate techniques which fuse with the base technique to successfully place match the particular query. We train a single network in our experiments using a combination of datasets to make predictions across several very different datasets, including 2 completely unseen datasets at test time. At inference time, our approach is slightly different. We perform VPR with the base technique to retrieve the top reference image according to that technique. We then use the base technique's descriptors for the query and top VPR match to generate a difference vector to use as input to our network. We then take the technique with the highest likelihood value at the end of the network as the predicted most complementary technique for that query to use in visual place recognition. For the actual place recognition, we use a multi-process fusion system, where we compute similarity scores between query image and the reference database for a base technique, and for our chosen predicted best technique, and then we normalize and sum the similarity scores. We can then take the highest fused similarity score as the best place match for that particular query. In our work, this table shows our quantitative results, which show that we're able to outperform logical naive approaches, such as using the best on average training pair, which for us was AmosNet and NetVLAD. We also show that we're robust to different environmental, structural, and viewpoint changes across very different datasets, as shown by our results on the SFU Mountain, Gardens Point Walking, Nordland, and Pittsburgh datasets. On top of this, we're able to successfully increase performance on completely unseen datasets, such as Robot Car Night and INRIA Holidays. On top of these results, we can use qualitative results such as these 2 figures here to show that our method is able to significantly reduce the amount of bad VPR matches across a dataset. In these figures, green bars denote queries which are successfully localized, and red bars denote failure points. It's important to also note that our method still does have failures, as indicated by the bottom rows in these 2 figures here. There are several other interesting findings that we had during our research, such as we found the network learned to only predict 3 of the 9 possible technique pairs. This was able to be explained by the fact that about 95% of training query images were localized with these 3 techniques plus NetVLAD. We also found a dominant technique pair was typically chosen for each dataset, likely explained by the fact that environment changes are typically consistent within each dataset and therefore suited to particular techniques. We also found that when you combine these into a single dataset, our method is able to successfully improve localization performance by switching between technique pairs without knowledge of the specific dataset or environmental conditions. Thank you for listening to my presentation on boosting the performance of a baseline visual place recognition technique by predicting the maximally complementary technique. Thank you.